LA Times is reporting experts are looking into whether it might raise the chance of a much larger event on the San Andreas Fault.
Scientists are warning that areas around the San Andreas Fault could see a strong earthquake as soon as this year.
NASA's startling revelation of a monstrous crack snaking through the San Andreas Fault has set off alarm bells worldwide. This isn't just any crack, it's a ticking time bomb, growing wider and more volatile by the day. The stakes couldn't be higher, as this colossal crack threatens to unleash unimaginable devastation upon unsuspecting cities. Join us as we delve into NASA's findings about the San Andreas Fault Crack and why it has people concerned. The San Andreas Fault, a ticking time bomb. Snaking for 800 miles along California's sun-drenched coast, the San Andreas Fault, a geological behemoth, has both fascinated and terrified generations. This colossal fracture, where the Pacific and North American plates grind against each other, conceals a terrifying reality. It is a sleeping giant, capable of unleashing apocalyptic earthquakes without warning. The history of the San Andreas Fault is written in the scars it has left on the landscape. In 1906, the fault ruptured violently, causing a devastating earthquake that shook San Francisco to its core. The magnitude 7.8 quake unleashed a wave of destruction, toppling buildings, triggering fires, and claiming the lives of over 3,000 people. The ground itself was torn apart, with some sections of the fault displacing by as much as 20 feet. But the 1906 earthquake was not an isolated event. The San Andreas Fault has been the source of numerous destructive earthquakes throughout history. In 1989, the Loma Prieta earthquake, with a magnitude of 6.9, rocked the Bay Area, causing 63 deaths and widespread damage. The collapse of a section of the Oakland-San Francisco Bay Bridge served as a stark reminder of the fault's destructive potential. As scientists study the San Andreas Fault, they have come to a chilling realization. The fault is overdue for another major earthquake. The accumulation of stress along the fault line, caused by the constant movement of the tectonic plates, is like a wound-up spring waiting to be released. The longer the interval between major earthquakes, the greater the potential for a powerful and destructive event. The question is not if, but when the next big one will strike. Seismologists warn that the southern section of the San Andreas Fault, which has not experienced a significant earthquake since 1857, is particularly vulnerable. This section of the fault, running through densely populated areas like Los Angeles and San Bernardino, could produce an earthquake with a magnitude of 7.8 or higher, causing widespread damage and loss of life. NASA's alarming discovery: a critical crack in the fault. In a startling revelation that sent shockwaves through the scientific community, NASA announced the discovery of a critical crack in the San Andreas Fault. Using advanced satellite imagery and cutting-edge radar technology, scientists uncovered a section of the fault that is experiencing rapid strain accumulation, with some areas showing a staggering 10-fold increase in stress buildup compared to previous estimates. The implications of this discovery are profound and deeply concerning. The rapid accumulation of strain along the fault line is like a rubber band being stretched to its breaking point. The more strain that builds up, the greater the potential for a sudden and violent release of energy in the form of a massive earthquake. NASA's findings paint a grim picture of the seismic hazard lurking beneath California's surface. The section of the fault where the critical crack was discovered, located in the Coachella Valley, has not experienced a major earthquake since the 17th century. This long period of seismic quietude has allowed stress to accumulate to dangerous levels, making the area a prime candidate for a powerful earthquake. But the alarming discoveries don't stop there. Scientists have also uncovered evidence of a previously unknown fault line running parallel to the San Andreas Fault. Dubbed the Salton Trough Fault, this hidden menace is capable of producing earthquakes with magnitudes up to 7.5, adding another layer of complexity and risk to an already precarious situation. The critical crack discovered by NASA is like a ticking time bomb nestled within the Earth's crust. As the Pacific and North American plates continue their relentless march past each other, the crack grows wider and deeper, the stresses within the rock building to a breaking point. It's a chilling reminder that the San Andreas Fault, for all its scientific intrigue, is a force to be reckoned with, a slumbering giant that could awaken at any moment with devastating consequences. The implications of NASA's findings extend far beyond the realm of scientific curiosity. The discovery of the critical crack and the Salton Trough Fault has forced a sobering reassessment of the seismic risks facing California. With millions of people living in close proximity to the San Andreas Fault, the potential for catastrophic loss of life and property damage is a grave concern. Beneath the surface, the science of the San Andreas Fault. To understand the true nature of the San Andreas Fault, we must delve into the complex and fascinating world of plate tectonics. The Earth's outermost layer, known as the lithosphere, is not a solid shell, but rather a jigsaw puzzle of massive rock slabs called tectonic plates. These plates, driven by the heat and convection currents emanating from the planet's interior, are in constant motion, sliding past, colliding with, or pulling away from one another. The San Andreas Fault is a manifestation of the relentless movement of two such plates, the Pacific Plate and the North American Plate. These geological behemoths are locked in a slow-motion dance, with the Pacific Plate grinding its way northward at a rate of about 2 inches per year, relative to its North American counterpart. This inexorable movement, driven by the vast forces deep within the Earth, is the underlying cause of the seismic activity that defines the fault. However, the San Andreas Fault is not a simple, straight-line boundary between the plates. Instead, it is a complex network of faults and fractures, each with its own unique characteristics and behavior. The fault system is divided into 3 main segments: the northern, central, and southern sections, each capable of producing powerful earthquakes, but with distinct patterns of seismic activity. The northern section of the fault, stretching from Cape Mendocino to San Juan Bautista, is characterized by a phenomenon known as fault creep. Here, the plates slowly slide past each other, releasing stress gradually through numerous small earthquakes and continuous, gradual movement. While this creep may help to prevent larger earthquakes in the short term, it is not enough to eliminate the risk entirely. In contrast, the central section of the fault, running from San Juan Bautista to Parkfield, is locked and prone to sudden, violent ruptures. This section is where the infamous 1906 San Francisco earthquake occurred. The southern section of the fault, extending from Parkfield to the Salton Sea, is perhaps the most enigmatic and concerning. This segment has not experienced a major earthquake in over 300 years, leading scientists to believe that it is overdue for a significant event. The Coachella Valley in particular has been identified as a seismic gap, an area where no large earthquakes have occurred for an extended period, allowing stress to build up to potentially dangerous levels. The behavior of the San Andreas Fault is influenced by a myriad of factors, from the type of rock it cuts through to the presence of underground fluids that can lubricate the fault plane. Even the weight of massive reservoirs like the Salton Sea can alter the stress patterns in the Earth's crust, potentially triggering or delaying earthquakes. The Looming Threat. Southern San Andreas Fault. In the sun-drenched expanse of Southern California, a sinister presence lurks beneath the Earth's surface. The southern section of the San Andreas Fault, a 730-mile stretch of geological instability, poses a grave threat to the region's inhabitants. This segment of the fault, extending from Parkfield to the Salton Sea, has been eerily quiet for over 300 years, lulling residents into a false sense of security. However, scientists warn that this prolonged period of seismic tranquility is not a cause for comfort, but rather a harbinger of a catastrophic event waiting to unfold. The Coachella Valley, a picturesque desert region known for its lush golf courses and music festivals, sits precariously atop one of the most dangerous sections of the southern San Andreas Fault. Beneath the valley's serene exterior, immense tectonic forces are at play, slowly but inexorably building up stress in the Earth's crust. The Coachella Valley segment of the fault has been identified as a particularly vulnerable area, with the potential to generate an earthquake of magnitude 7.8 or higher. To put the scale of such an event into perspective, a magnitude 7.8 earthquake would release energy equivalent to detonating 1.1 gigaton of TNT, or roughly 73,000 times the power of the atomic bomb dropped on Hiroshima. The shaking from an earthquake of this magnitude would be felt across an area of 50,000 square miles, with the potential to cause catastrophic damage to infrastructure, buildings, and lifelines. One of the most chilling aspects of the southern San Andreas Fault's seismic potential is its proximity to densely populated urban centers. Just 50 miles to the west lies the sprawling metropolis of Los Angeles, home to over 10 million people. A major earthquake on the southern San Andreas Fault could have devastating consequences for the city, with the potential for widespread destruction, loss of life, and a crippling economic impact that would reverberate across the nation. The U.S. Geological Survey (USGS) has developed a chilling scenario known as the shakeout, which simulates the effects of a magnitude 7.8 earthquake on the southern San Andreas Fault. The scenario paints a grim picture: over 1,800 deaths, 50,000 injuries, and $200 billion in damage. Bridges would collapse, roads would buckle, and buildings would crumble, leaving a landscape of destruction that would take years, if not decades, to recover from. However, the threat posed by the southern San Andreas Fault extends beyond the immediate impact of ground shaking. The fault's proximity to the Salton Sea, California's largest lake, raises concerns about the potential for a seismically induced tsunami. Although tsunamis are more commonly associated with offshore subduction zones, recent research suggests that a large earthquake on the southern San Andreas Fault could trigger underwater landslides in the Salton Sea, generating waves up to 30 feet high that could inundate surrounding communities. Now it's time for today's subscriber pick. Recently, a warning has been issued by NASA: San Andreas Fault Crack on the brink of eruption. This alert has reawakened fears of the big one, a catastrophic earthquake of unprecedented magnitude. Experts warn that this geological time bomb could rupture with devastating force, unleashing a seismic apocalypse across California. Densely populated regions like Los Angeles and San Francisco are particularly vulnerable, with predictions of widespread building collapses, shattered infrastructure, and countless lives lost. What are your thoughts on this impending crisis? Let us know in the comments. Dried up lakes, a surprising seismic influence. In the arid landscapes of Southern California, a series of long-forgotten lakes holds a surprising key to understanding the region's seismic past and future. These desiccated basins, known as playa lakes, have been proposed as unlikely culprits in the complex interplay of factors that influence the behavior of the southern San Andreas Fault. While the concept of ancient lakebeds exerting control over the movement of tectonic plates may seem far-fetched, a growing body of scientific evidence suggests that these ephemeral bodies of water could play a critical role in modulating the fault's seismic activity. Playa lakes are shallow, ephemeral bodies of water that form in arid environments when rainwater or snowmelt accumulates in low-lying areas with poor drainage. Over time, as the climate shifts and temperatures rise, these lakes evaporate, leaving behind expansive salt flats and sun-baked clay. The Salton Trough, a vast sedimentary basin that stretches from the Coachella Valley to the Mexican border, was once home to a sprawling network of playa lakes that covered an area larger than the state of Rhode Island. Recent studies have proposed a fascinating link between the cyclical filling and drying of these ancient lakes and the behavior of the southern San Andreas Fault. The idea is that the weight of the water in the lakes, which can amount to billions of tons, exerts a significant load on the Earth's crust, altering the stress patterns and frictional properties of the underlying fault. When the lakes are full, the immense weight of the water acts as a sort of seismic suppressant, clamping down on the fault and inhibiting the buildup of tectonic stress. This phenomenon is similar to how a heavy book placed on a creased piece of paper can prevent the paper from folding along the crease. In the case of the southern San Andreas Fault, the presence of water-filled playa lakes may have helped to prevent large earthquakes by keeping the fault locked and unable to rupture. However, as the lakes dry up, this stabilizing force is removed, and the fault is free to move more easily. The reduction in water weight can cause the crust to rebound, altering the stress patterns and potentially triggering a release of pent-up seismic energy. It's like removing the heavy book from the creased paper, allowing the fold to snap into place suddenly. One of the most intriguing examples of this lake-fault interaction is the story of Lake Cahuilla, a massive body of water that once filled the Salton Trough. During the last glacial period, around 20,000 years ago, the Colorado River flowed into the Salton Trough, creating a vast inland sea that covered an area of 2,000 square miles and was over 300 feet deep. The weight of this immense volume of water would have exerted a significant downward force on the Earth's crust, potentially altering the stress patterns on the nearby San Andreas Fault. As the climate warmed and the glaciers receded, Lake Cahuilla began to evaporate, its waters slowly vanishing into the desert air. The lake underwent a series of filling and drying cycles over the millennia, with the most recent desiccation occurring just 400 years ago. Scientists have noted a curious correlation between the timing of these drying events and the occurrence of large earthquakes on the southern San Andreas Fault, leading some to speculate that the disappearance of Lake Cahuilla may have played a role in triggering these seismic events. Today, the Salton Sea, a remnant of the ancient Lake Cahuilla, is a focal point of both environmental and seismic concern. The lake, which was accidentally created in 1905 when a canal breach diverted the Colorado River, has been gradually shrinking due to reduced inflows and increased evaporation rates. As the lake recedes, it exposes vast expanses of lakebed sediments that are rich in toxic metals and pesticides from agricultural runoff. The drying of the Salton Sea not only poses a significant environmental and public health risk, but may also have implications for the seismic hazard of the region. As the weight of the water is removed, it could potentially alter the stress patterns on the nearby San Andreas Fault, increasing the likelihood of a large earthquake. Monitoring California's seismic pulse. In the face of the ever-present seismic threat posed by the San Andreas Fault, California has become a hotbed of cutting-edge earthquake monitoring and research. The USGS, in collaboration with a network of academic institutions and government agencies, has deployed a sophisticated array of seismometers, GPS stations, and other monitoring technologies to keep a watchful eye on the state's seismic pulse. One of the USGS's most critical tools in the fight against earthquakes is the network of over 8,000 seismometers that blanket California. These highly sensitive instruments, which can detect even the faintest vibrations in the Earth's crust, provide scientists with a real-time stream of data on seismic activity. By analyzing the patterns and characteristics of the seismic waves recorded by these devices, researchers can paint a detailed picture of the stresses and strains accumulating deep within the Earth. But seismometers are just one piece of the puzzle. To fully understand the behavior of the San Andreas Fault and other seismic hazards, scientists must also track the slow, gradual movements of the Earth's crust over time. This is where GPS comes into play. By continuously monitoring the positions of hundreds of GPS stations across California, researchers can detect minute changes in the distance between these points, revealing the inexorable creep of the tectonic plates. The data collected by these seismometers and GPS stations is fed into sophisticated computer models that simulate the complex interactions between the Earth's crust and mantle. These models, which are constantly being refined and updated as new data becomes available, help scientists to identify areas of heightened seismic risk and to forecast the likelihood and potential impact of future earthquakes. But monitoring California's seismic pulse is not just the province of the USGS. A wide range of academic institutions and research centers are also actively involved in the effort to understand the state's earthquake hazards. The Southern California Earthquake Center, SCEC, a consortium of over 60 universities and research institutions, is at the forefront of this collaborative endeavor. SCEC brings together experts from a wide range of disciplines, including seismology, geology, engineering, and computer science, to tackle the complex challenges posed by earthquake science. The center's researchers use advanced computational tools and data analysis techniques to simulate the behavior of faults and to develop detailed seismic hazard maps that inform land use planning, building codes, and emergency response strategies. Lessons from California's earthquake history. California's seismic past is a tapestry woven from the threads of tragedy, resilience, and hard-won wisdom. Each major earthquake that has struck the state has left an indelible mark on its landscape and its people, offering sobering lessons about the destructive power of the Earth's tectonic forces and the urgent need for preparedness. One of the most devastating earthquakes in California's history struck San Francisco on April 18, 1906. With a magnitude of 7.8, the quake unleashed a wave of destruction that swept through the city, toppling buildings, rupturing gas lines, and igniting fires that raged for days. The human toll was staggering. Over 3,000 lives were lost, and more than 200,000 people were left homeless. But the lessons of the 1906 quake went beyond the immediate destruction. The event exposed the inadequacies of the city's building codes and construction practices, which had failed to take into account the seismic hazards of the region. In the aftermath of the disaster, San Francisco embarked on a massive rebuilding effort that laid the foundation for the modern seismic safety standards that have since become a model for cities around the world. Nearly a century later, the 1994 Northridge earthquake delivered another powerful blow to California's sense of seismic security. With a magnitude of 6.7, the quake struck the heart of the San Fernando Valley, just 20 miles northwest of downtown Los Angeles. The shaking was intense, with peak ground accelerations reaching 1.8 times the force of gravity. The earthquake caused widespread damage to buildings, bridges, and other critical infrastructure, with losses totaling over $20 billion. The Salton Sea Dilemma: balancing environmental and seismic concerns. In the desert landscape of Southern California, the Salton Sea has long been a flashpoint of environmental and public health concerns. This vast, landlocked body of water, which spans over 340 square miles, has been grappling with a host of ecological challenges in recent years, from rising salinity levels to the loss of critical habitat for migratory birds. But as scientists and policymakers seek to address these pressing issues, they must also confront a surprising and often overlooked threat: the potential seismic consequences of efforts to rehabilitate the sea. The Salton Sea's troubles began in earnest in the early 2000s, when a series of agreements led to a reduction in the amount of water flowing into the sea from agricultural runoff. As the sea's water levels began to drop, vast expanses of lake beds were exposed, creating a dystopian landscape of salt flats and decaying fish carcasses. The receding shoreline also exposed centuries of accumulated agricultural chemicals and other pollutants, which were picked up by the wind and carried into nearby communities. The public health implications of the Salton Sea's decline are staggering. The airborne particulates from the exposed lakebed have been linked to a range of respiratory illnesses, including asthma and bronchitis, with children and the elderly being particularly vulnerable. In some communities near the sea, emergency room visits for respiratory issues have spiked by as much as 50% in recent years. Efforts to address the Salton Sea's environmental and public health challenges have been complicated by the surprising discovery of a potential link between the sea's water levels and seismic activity along the southern San Andreas Fault. Recent studies have suggested that the weight of the water in the Salton Sea may be acting as a sort of hydraulic jack, exerting pressure on the Earth's crust and potentially influencing the behavior of the nearby fault. The implications of this discovery are profound. Any efforts to rehabilitate the Salton Sea, such as importing water from other sources to maintain water levels, could inadvertently alter the delicate balance of forces that have kept the southern San Andreas Fault in check for centuries. By changing the weight distribution on the Earth's surface, these interventions could potentially trigger a seismic event of catastrophic proportions. At the same time, allowing the Salton Sea to continue its decline unchecked is not a viable option. The environmental and public health consequences of inaction are simply too grave to ignore. Policymakers and scientists are therefore left with a daunting challenge: how to balance the urgent need to address the sea's ecological crisis with the potential seismic risks of intervention. Any successful approach to the Salton Sea dilemma will require a multidisciplinary effort that brings together experts from a wide range of fields, including ecology, public health, seismology, and geotechnical engineering. It will also require a willingness to think creatively and embrace innovative solutions that may push the boundaries of conventional wisdom. One potential approach that has gained traction in recent years is the idea of using geothermal energy production to stabilize the Salton Sea's water levels. The sea sits atop a vast geothermal resource, with hot brine and steam bubbling up from deep beneath the Earth's surface. By harnessing this energy to power desalination plants and other water treatment facilities, it may be possible to create a self-sustaining system that balances the needs of the environment with the imperatives of public health and safety. The consequences of a major earthquake and preparing for the inevitable. The specter of a major earthquake along the San Andreas Fault looms large over California, casting a shadow of uncertainty and dread across the state. With each passing year, the likelihood of a catastrophic seismic event grows, and the potential consequences become ever more dire. From the dense urban centers of Los Angeles and San Francisco to the vital agricultural regions of the Central Valley, no corner of the state is immune to the devastation that a powerful earthquake could unleash. The sheer scale of the potential damage is staggering to contemplate. A magnitude 7.8 earthquake rupturing the southern section of the San Andreas Fault could cause over 1,800 deaths, 50,000 injuries, and a staggering $200 billion in economic losses. Bridges would collapse, hospitals would be overwhelmed, and vital lifelines like water, power, and communication networks could be severed for weeks or even months. However, the consequences of a major earthquake would extend far beyond the immediate zone of destruction. The ripple effects of such a disaster could be felt across the entire state and beyond, disrupting supply chains, choking off vital transportation corridors, and sending shockwaves through the global economy. In a worst-case scenario, a major earthquake could plunge California into a prolonged period of chaos and hardship, testing the limits of the state's resilience and resources. Faced with such a daunting threat, it is tempting to succumb to a sense of fatalism or despair. But while the risk of a major earthquake is very real, it is not an inevitability. California has made significant strides in recent years to enhance its seismic resilience, from strengthening building codes and retrofitting critical infrastructure to investing in cutting-edge monitoring and early warning systems. At the forefront of these efforts is the California Governor's Office of Emergency Services, Cal OES, which is responsible for coordinating the state's preparedness and response activities. Cal OES has developed a comprehensive strategy for mitigating the risks posed by earthquakes, including the deployment of a statewide network of seismic sensors, the development of detailed response plans and protocols, and the coordination of training and exercise programs for emergency responders and community members alike. However, preparing for the inevitable requires more than just top-down planning and coordination. It also demands a grassroots commitment to seismic safety and resilience, one that engages individuals, families, and communities in the hard work of building a more earthquake-resistant future. This includes simple steps like securing heavy furniture and appliances, stockpiling emergency supplies, and practicing drop, cover, and hold-on drills. It also means supporting policies and investments that prioritize seismic safety, from retrofitting vulnerable buildings to investing in research and innovation that can help us better understand and mitigate the risks posed by earthquakes. The key to surviving and thriving in the face of California's seismic hazards lies in a combination of individual preparedness, community resilience, and forward-thinking policies and investments. By working together to confront the challenges posed by earthquakes, Californians can not only reduce the risks to life and property, but also cultivate a culture of readiness and resilience that will serve the state well in the face of any future crisis. Thanks for watching, and we'll see you in the next one.